Hello. This session of conference it's about text classification, and we've got 4 papers. 2 of them will be presented here, and the last 2 of them will be the first one a video and the second an online presentation. So we are going to start with item Salat with the paper entitled Adapting Transformers to Multilabel Text Classification.
Hello. So hi everyone, I'm Aitan Salat. I'm a PhD student at Aix-Marseille University, team Technology Mediums, University of Toulon. Patrice Pelot, Elisabeth Massasco, and Manuel Bueno are the co-supervisors of this PhD. I'm going to present you adapting transformers for multilabel text classification. So the PhD started last year. It's a CFO PhD with a startup called Hypervirus. It's a startup that uses deep learning methods for different domains like computer vision and text classification. So this project is with an insurance agency that wants to classify their mail, incoming mail from their clients. And these kind of mails can have multiple subjects. So we have to classify the mail, determine all the subject that is in the mail, and then trigger the corresponding actions with those subjects. So we have to route the mail to the corresponding person, generate some answer if we can, and trigger some automatic actions. So what's the difference between multilabel and multi-class? In multi-class classification, classical one, the input is assigned one single label from a set of labels. In multi-label classification, an input can have multiple labels from a set of labels. It's a task that is unfortunately not very present in most reports, but despite having very important real-world applications like content recommendation, metadata extraction, and recently I've seen like an application in chatbots to conversational AI. And the constraints of the project are also in the context of mail. Sorry, there are different writing styles. Like each client will have a style of writing that is different from the other, and different level of expertise also. We have persons that are talking about a specific domain with different levels of expertise. So there are 3 major techniques for multi-label classification. The first one is the problem transformation, where we transform literally the problem from a multi-label to a multi-class classification. Some methods like we take all the combinations that are possible from the labels, and we train a classifier to classify these each unique combination. The problem with this is that the training is very costly. If the number of labels is big, the training is very, very costly. The second method is the ensemble methods, where we train multiple classifiers for each label. So for each label, there will be a classifier that would say if the label is present or not. For this method too, it is very costly because we train multiple classifiers to do one single task. The third one is the problem adaptation, where we adapt architectures and models for the multi-label problem. This is very efficient because we have one classifier and we have just the set of labels that we begin with. So recently in NLP, transformers have been the state of the art. Transformers are simply just models that contextualize the input embeddings throughout the layers and throughout the training. So we end up at the end with contextualized embeddings. Each word is assigned to a token, of course, and an embedding that have an embedding that is dependent on other embeddings that are in the sentence. And BERT is one of these transformers that introduces a special token here, the CLS token, that aims to have a representation, a full representation of the sentence. So an embedding that includes all the meaning of the sentence. So in text classification and also in multi-level classification, we use this token, the CLS token, as input for the classification. So we add a multi-layer perceptron after the CLS token, and train this multi-label perceptron as well as the whole transformer for the classification. So it's not in multi-level classification, it's not very different from classical classification. What's different is the activation function at the end and the cost function. So the cost function will be the binary cost interpret, where each label will be a value between 0 and 1. And to do that, we have the sigmoid function. So we have a threshold, 0.5, which is the threshold that is used very often. If this threshold is, if we go above this threshold, we consider that the label is present. So in this paper, we have used many variants of BERT, notably Roberta, which is a variant of BERT that is trained on 10 times bigger, the corpus that is 10 times bigger. We have the Silbert, a smaller version of BERT, that uses knowledge distillation. The Berta, that is one of the recent variants of BERT that we will discuss later. And Camembert and Flaubert, that is two variants of BERT that are trained on French data. So the first contribution in this paper is the creation of a new multi-label data set, a French one, because there are not many French multi-label data sets, and we saw that this is a very good contribution to make one and make it available for people to test their models in French from French data sets. We also tested on two other data sets that are very well known in the multi-level scene. IAP, which is an abstract comprised of abstracts of computer science articles from archive, and Reuters and the news articles from Reuters. So first, we tried some thresholding methods to increase the performance of the components from the test. There are two main methods for thresholding. The first one is to calculate a global classification threshold. We will have one threshold that will be calculated for all the labels. So this threshold will be calculated at the training time. Why we calculate a new threshold and not 0.5? Because sometimes the training is not done very well, and we can have a label that is present, but have an activation of 0.4, or have an activation of 0.6, really, but not present in the sentence. So we calculate a new threshold from the training set, a threshold that will be optimizing whatever metric we are trying to optimize. So the first one is to have a global threshold for all the labels. The second one is to calculate a threshold for each. So these methods have some good results, especially when we compare we have used the base version of all the transformers mentioned earlier, and we obtained performance that is better in some cases than Doppler and BERT large, which is a very much bigger model that is very. We have then introduced some two techniques to try to avoid these thresholding methods. And the first one is to simply add an additional layer to the classifier. The reason behind this is to try to capture, to capture the dependencies that can exist between the labels. So what we do here is we have two separate optimizers, one optimizer for the last layer that we have added, and another one for the whole model that comes. And we train the truth and the true layers that are at the end of the model. Each layer has its own objective, is to try to detect to predict rather the label that is present. And we think that by doing this, not also we can include the dependencies that can exist between the labels, but also try to learn these thresholds. Not try to get them in the training data set or in the test data set in some cases, rather to learn them. So this method, unfortunately, might be interesting, but unfortunately doesn't get the same performance of thresholding methods, but it is very competitive. It has, in some cases, the same results like BERT large. So we train the base version of BERT and its variant, and we have better performance than the larger version of BERT. The second method, which is an interesting one too, is to try to predict the number of labels that are present. So we introduce a new neuron that will try to predict what number of labels that are present, and then take the n highest activation from the rest of the activations to say that those activations are the ones that we are looking for. Unfortunately, it is, although it is an interesting method, it does not yield very good performance. Because we think that the CLS token alone does not contain this kind of information. So problem adaptation is clearly the way to go, and it is very efficient from the other methods. And this method that we have introduced can be used not only for text classification, but other domains. What we can do next is try to pre-train BERT on specific domains, like the insurance data, look for other ways to calculate the number of labels, but also try to find better ways to include the dependencies that can exist between domains. So, thank you. Any questions? Yes.
Thank you for the talk. In the starting point, when we have multi-layer, do you have a flat organization or you actually have one?
Variables. Yeah, these are two. Very good question, thank you. In some cases, in some data sets, it is a flat one. In some other data sets, it's a hierarchical one. In what we have studied in this paper are flat ones. So hierarchical multi-label classification is another subject. It's a very complicated one as well, but it's very interesting. And we think that in my PhD, I will focus on this subject of hierarchical representation of the labels.
Hello, thank you. Maxime Street. Did you try combining the thresholding methods with the other two methods to see if the three put together?
Yeah. So The idea behind the two other methods is to alleviate the need for thresholding methods. So we didn't seek to additionally to apply these thresholding methods to these methods because the whole goal was to avoid them. So.
Yes, thank you for the presentation. Just a quick question. I do a lot of comparison between classification method and generation methods to generate a stream of. And so did you try to see the performance if you use a part or part or one of these models to generate the sequence of labels?
Generate the sequence of label and use those embeddings for the classification model?
We won't directly reproduce generate the translation process, only directly to the representation to the labels.
Sorry. Yeah, it's very interesting. No, we haven't tried this for the moment, but it's very interesting. Yeah. Thank you. Thank you for your suggestion.
Any other question? Do you think that the performance of your models are going to be the same more or less when you apply them to your specific domain in about email?
I certainly hope so. Yeah, maybe
But
better.
do you think that the domains are different because and the problems that you're going to face in this email multi-label classification are not going to be the same?
It's certainly different from the first data set, which is IPD, it's the abstract of scientific articles, but it's not that different from Reuters, which is news articles, which is much lower complexity, I would say. I feel confident in the performance that we can obtain in this data set. The insurance. Thank you.
There are no more questions, and thank you.
Thank you.
Second paper this morning is entitled Deep and Ordered Composition for Multi-Label Classification Applied to Skills Prediction, and it's going to be presented by Jan. What's your name? How do you pronounce?
Jan de Bel.
Yeah.
Thank you.
Good morning, everyone. Can you hear me well? Not too loud, not too. Okay. First of all, thank you for attending this short presentation about our long paper, which is entitled Deep and Ordered Composition for Multi-Level Classification Applied to Skill Prediction. This article has been written by myself, Yann Duperret, and Adrien Clifou, Bernard Espinas, Sébastien Fournier, and Arthur Kuhn. Okay, so first of all, as you can notice in the title, this article is about skill prediction. So I will start by presenting the problem. What is skill prediction and why do we need it? Okay, so let's start with a simple observation. The digitization of recruitment processes has increased the number of applications and available documents online, whether it is job offers or resumes or even professional profiles on professional networking platforms, which are used for searching for candidates and filtering the application, which have become very consuming, very time-consuming, activities for recruiters. And these activities do not have any added value. So a few decades ago, a lot of research work started to try to alleviate this problem by providing recruiters with automated systems to help matching job offers with candidates. However, most of these existing solutions do not yield appropriate results when they are applied to specific activity sectors or profile level jobs, expert level jobs. So the goal of my PhD, because I'm a PhD student at Aix-Marseille, by the way, the goal of my PhD is to address this problem by conceiving a job recommender system specialized for specific sectors. In the case of our industrial partner, the energy sector, and for expert level jobs. Okay, so our research work started with a very simple observation, which came from the state-of-the-art and our numerous talks with the recruiters who are partner in this project. We noticed that most human recruiters and some of the automated systems of the state-of-the-art use skills to evaluate matching between job offers and candidates, which seem kind of obvious when you think about it, but it's not that obvious and trivial when you have to do it. Researchers have also shown that candidates usually, always even, do not declare all their skills in their professional resumes. They can omit some skills because they think they are implicit for domain experts, or they can simply just save space in the professional profile. It's really trivial, but it's a big problem for an automated system because the information is not there. So if we want to build an information retrieval system for this kind of documents that relies on skills, well, we have to pre-process the documents to detect those skills, and this is the skill prediction, or sometimes called skill inference task. And this paper presents a method to tackle this task with the following hypothesis, which is the text written in a professional profile is a good predictor of the skills owned by the individual. And when I say the text, what I meant was the terms, the most significant terms, which are domain-specific terms. So it's a lexical approach, but I'll explain this later. Okay, so let's dive into our proposed method, which starts by a little shift, an adaptation of the problem of skill prediction. If you think about it, it seems obvious that, which is not, that skill prediction is a multi-level classification task. You have some models, some algorithm, which take as input a text, however it is represented, and output all the possible labels, which are the skills in a vocabulary, and assign them scores. 0 if the skill is not owned by an individual, 1 if the individual has the skill. However, to answer the previous question, in our work, there are relationships between the skills. So we can have taxonomies or hierarchies or other kind of semantic relationships, but that are very often implicit. We know they exist. They are very important for the prediction. As an example, we can say that if an individual has a set of skills, it is highly likely that he will have other skills. And we have a lot of labels. Actually, in this task, we have one label per skill. And if we have a big vocabulary of skills, like the European Ontology of Skills and Competencies, which is named ESCO, it's a European reference published in 2012, we can have thousands of skills, so thousands of labels. Such extreme multi-level classification tasks are notoriously hard, so we propose to adapt the problem by what should I do? Thank you. Sorry for the interruption. I did not notice there was a problem. But thank you. You have been very calm. Okay, so we decided to shift our problem to a multi-level classification task to binary classification task. So how did we do it? Well, we decided to make the skill to which ownership is to be inferred not as an output of the model, but as an input. So our model takes as input the text of the profile and the skill to evaluate. And the model predicts the binary prediction whether the profile has the skill or not. Okay, so now that I've presented you the task, I've told you that we were working on profile text. So now I'm going to develop this part. How do we handle the text? Well, there are two ways to do it. Actually, with the current state of the art in natural language processing, we can use big complex models that are often called syntactic deep learning models, like transformers, for example. Those models achieve state-of-the-art performances. However, they have few shortcomings. First of all, those models are highly complex. They require a lot of computation and memory, and also a lot of data to be trained or even fine-tuned. And they can only exploit short spans of text. Although there are some solutions that exist, like hierarchical approaches like HIVERT. However, our problem is that professional profiles are usually too big to fit in those contexts. So we have to find other solutions. On the other hand, we have other types of architectures that did not gain the traction that the transformers gained, which are models based on deep unordered composition approaches, which totally lose the order of words and syntactic information. However, this kind of model still achieves interesting performances on some NLP tasks. The most known of these models is DAN, Deep Averaging Network, which has been published in 2015. It's an example of such an architecture where the input words are simply, the embeddings are simply averaged and then projected into a further latent representation for, well, depending on the task, it can be classification. Actually, it works for some tasks. So we were inspired by this kind of approaches and decided to research alternatives that rely on a deep and ordered composition. So we find another kind of transformer, which you might not have heard of, which is the set transformer, which has been published in 2019. It's simply a transformer without positional encoding. So this transformer has no idea of order of its inputs and is permutation invariant. So we decided to try to use it to handle the text of our profiles, and we evaluated along with Dan to ingest the text of our profiles. Okay, so since we don't care about the order of the words, and like I told you, we use a specific domain term to perform the prediction. We use a bag of word representation. To be more accurate, we simply use TF IDF to score every term in our documents, and we select the 100, 200, 300, it's an hyperparameter, but we select a few hundred terms with the highest TF IDF score, and we use these terms as inputs of our deep and ordered composition-based model. Okay, so let's dig deeper into our proposal. So you can see the whole architecture of the model. So as I told you, the most important part is the profile encoder, which is a module responsible for producing a latent representation for profile based on its text represented as bag of word. So this module has two possible implementations. So one based on DAN, deep averaging network, and one based on the set transformer architecture. The other important input is the skill to evaluate, which we represent as an embedding, so as a vector. Okay, I will try to go faster. So we combine the two latent representations, further project this representation, and then apply a binary classifier, so simply a dense layer with a sigmoid activation function, and based on the threshold, we decide whether it is positive or negative. Here you have a few examples of the embeddings. So I will skip this part. Here you have an example of the model used, so you can see the terms. We insert the terms of the profile in the profile encoder. We insert the skill in the skill encoder. We retrieve latent representation that are further propagated into the network. Okay, so to evaluate if our method was working, we evaluated it on a public profile data set that contains 30,000 profiles with a total of 1,000 scales. So we use this data set it's a small data set, but it's really hard to find such kind of data set. We used it to train and evaluate our model to answer the following research question. Can a deep and ordered composition-based model capture meaningful information from text to perform this skill prediction? Can very specific rare skills be predicted with this approach? And finally, is the usage of classes as model inputs in a binary classification task as a proxy for a multi-level classification task works? Okay, so here are the results, and after that, it will be done. So we did not have a baseline because it's kind of hard to find a comparison on data sets that are not used and where there are no benchmarks. So we evaluated different variants of our model and tried to evaluate them absolutely without reference. So you can notice that we have a strange term named number of invalid classes. Well, we observed that sometimes some classes we still don't know why just can't be run by the model. It might be a problem with the data sets and overfitting. It might be an artifact or a more profound problem. To be honest with you, we don't know yet. We need to research the problem a little bit further. So each model has a number of invalid classes that is different. So since these classes can be easily identified, we simply decided to remove them and to perform an evaluation without them, which yield the following results. You can also see for the best model, the metric distribution, classic distribution for binary classification across all classes. Okay, so discussion. We observe that the model distribution is wide, meaning that our model works very well for some classes, and for some others just don't work or we can't be confident enough. We also observed manually that for some very rare skills, the model still achieves very good performances, which is very encouraging for us. So as I said, this is really preliminary work on this approach to multi-level classification with a lot of labels semantically linked. And we consider these results to be encouraging, and they can help close the gap between skills declared in profiles and skills required in job offers. So future work will certainly enhance this method, apply it to a job recommender system, or even try to apply it to other text multi-level classification tasks. Okay, that's thank you. If you have any questions, I'll gladly answer them, and sorry if I took too much time.
As far as I understood, the skills are also represented by text or not?
No, I represented them as text in the embeddings slide, just to show that we embed them and that with these embeddings we are able to place them in a high-dimensional space relatively to their semantic relationship. But no, they are not text at all. Actually, we could simply replace them with ideas. They are more like concept. Actually, we consider them like concept. However, they are written, to us, it's concept.
I was thinking that if they were associated these text, these terms, maybe you can try an IR-based approach in order to test, to compare with your
Okay.
models, just a baseline.
I did not say it, but when we detected skills, we removed them from the text for training and evaluation to avoid simply comparing ourselves to an extractive method. We do not extract the skills from the text, we predict them. So we remove every textual traces of the skill from our training dataset and evaluation dataset.
Any other question? Thank you very much.
Thank you.
Now the next paper is a video and it's titled Text Clustering Based on Multi-View Representations by Eya Amami and Rim Pai.
So she will be there for the questions, but we prefer to run the video. Si je mettais ma machine. Ah oui, parce qu'il faut changer la machine. Pardon.
Hello, good morning, everyone. Hope that you are doing fine. So I'm Amy Manning, a PhD student.
Questions?
Thank you. Can you hear?
Yes.
Okay. Just to know, how do you choose your different sentence web models? Are there fine-tuned on different data, or what is the to what is the notion of multi-view correspond in class?
I couldn't hear it. Could you please repeat the question?
How do you select your different sentence web models?
Okay. Okay, I selected them. Actually, I tried all of the SBERT, the majority of the SBERT pre-trained models, and the models that they give me good results according to the poverty, NMI, and the F-measure metric. I use them to implement the proposed model, which is the multi-view clustering. So,
Was it trained
and
on
also,
were they trained on different data? Do they correspond to different applicative domains, or what is the difference between them?
I tried just the BBC News data sets. Is this a question? Is this the question?
The sentence web models
Yes.
are they trained on the different data, or are they just what is the difference between them?
What is the difference between the pre-trained SBERT models?
Yes.
Okay. Actually, the SBERT pre-trained models, there are some pre-trained using some special language. For example, some pre-trained models for the Dutch language or for the French ones. But in my case, I use just the models that are trained on English corpus. Okay. Then also I use the pre-trained models that are trained on clustering tasks. Okay. Could you hear me?
Yes.
Hello? Have you considered using the text summary instead of the whole document or the clustering? Hello? Can you hear us?
No, maybe you should. Thank you.
Yeah. Can you hear me now?
I couldn't hear you.
Oh, no?
Yeah, the microphone is
Okay.
good. That's good. You can
Speak.
stay.
So, can you hear me now?
Yeah, yes.
Have you considered using the summaries of the texts rather than using the whole document for the clustering text? Or have you used the entire document? Because I think it can be much more efficient.
I used the summary of the texts.
Have you considered using summary?
I used actually the whole of the text, not the summary of the text.
Have you considered it? Oh,
So did you make the same experiments while using the long text, just
Yeah.
using the summaries or the abstracts?
Okay, but actually, the problem of BERT's models are the max language, so we can't use it for long texts. So we should I think we should adapt this model to for the long texts. So this is the question. Is it the good response, or not?
I know. Thank you.
Is it the good response for your question?
Yes.
Any other question? I've got one. I would like to know if you have compared your approach with classic k-mean clustering in order to determine if the transformers that you have used have a positive impact on the clustering process. Have you heard me? Hello?
Hello?
Can you hear me?
Yes, yes.
I was asking if you have compared your model with classic k-mean clustering in order to evaluate the impact of your transformers.
Yeah, I compared it. Actually, in this work, we tackle just the comparison between the single view clustering method using k-means and also the multi-view clustering using the k-means also. And all of both of these methods, we use the SBERT as a pre-trained, as an embedding layer.
Okay. Okay. Hello? Yeah. Okay. Thank you very much. Any other question? Okay. Thank you.
Time to present the latest one. Give me the time to. Oh, it's YouTube. Wait, 2 seconds. Still 2 seconds. No, he's not going to open now. I have to. So many things to do. I have to share the screen. Where is it? Here. C'est celui-là? Oh là là, pardon.
Hello, can you hear me?
Yes. Oh, but yeah. So,
Hello? Yeah.
Who is the next speaker?
Andrea.
Okay, so he's here. Yes. Can you share your screen, please?
Yes. Check. Okay, I think I should be sharing the screen now. Do you see?
That's perfect.
All right. Just tell me when to start.
Algorithm evaluation, and is presented by Andrea Alessio Molina.
Yeah. Can I start?
Yes.
All right. Hello, everyone. So I'm Alessio Molinari, and I will be presenting this paper, Active Learning and the SLD Algorithm. I'll be super quick because there's a lot of stuff, so I won't have time to go into details, but you can ask me after the presentation. So basically, in many classification tasks, we suffer from prior probability shift, and this means that our prevalence that we have on the unlabeled set might be very different from the prevalence that we have on the labeled set. And when this happens, a classifier that is trained on the training set might output posterior probabilities that could be of a rather poor quality. Can we do something about this? Well, the Cerens and Latin de Castegar algorithm, also known as expectation maximization for quantification, is a rather old iterative algorithm, but it's still the state-of-the-art technique to adjust both the prior and posterior probabilities in PPS scenarios. And basically, this is how we update our posterior probabilities, where I would ask you to focus mainly on this one. This is like the estimated prevalence, so it's the average of the posteriors. I told you I won't go into too many details, but after we run SLD, we get a new set of posterior probabilities, and hopefully this is better than we had before running SLD. The pre-SLD posteriors are coming from our classifier. So we want to see how this performs when we do active learning. And by active learning, we mean a technique which we use to prioritize documents for review. So we have an unlabeled pool of documents D, and we need to decide which documents we review and which documents we don't. And the two most famous techniques are relevant sampling, where we show basically the top K documents ranked according to a classifier, and the uncertainty sampling, where we show basically the documents that the classifier is most uncertain about. So we also define an oracle-like policy, which we call RAND, where basically after we run the active learning technique, we know that we have generated a prevalence on the training and on the test set. So we do a random sampling where we actually control this prevalence such that we generate another training and test set with the same prevalence that the active learning generated. We do this because we want to see if the results that we are seeing are due to the prevalence shift that we are seeing, or maybe to the document selection policy, because in this case, it's completely random. It's not decided by a classifier. So in active learning scenarios, we have a very high shift, and we might think that using SLD could be a good idea. But in some previous research, we also noticed that these two techniques combined together don't really work well. So we want to clarify, if possible, what happens when you combine these two techniques. So we basically use the relevance and uncertainty sampling active learning to generate several training sets with different sizes. And we obtain an equal amount of training and test sets with the RAND policy that I was telling you about. And then we train an SVM classifier. We calibrate it to obtain posterior probabilities, and then we apply SLD. We evaluate the posteriors in terms of like a lot of known metrics. But I won't show you results here because, again, I don't have too much time. But do notice that the results show that SLD deteriorates both the prior and posterior probability distributions. And this does not happen for the RAND policies. So it is most likely due to the document selection policy and not to the prior probability shift. Our hypothesis is that this might be due to sampling bias, because when we do active learning, we tend to prioritize documents which might be very similar. Like if we imagine the data distributed on a 2D plane, maybe we are only taking positives on a small region of the graph. And when this happens, it might be that the classifier can be very sure of the items label, so it's very biased. And if the dataset is unbalanced towards the negative class, as it is usually the case, then the estimated prevalence for the positive class will be basically close to 0. And if you remember the equation I showed you before, like this is very trivial. Like when this goes to zero, then everything goes to 0. And indeed, if you look at the posterior probability distribution that we have before and after SLD, you see that basically when we do active learning, the posterior are very skewed towards 0 already, and SLD is basically destroying the probability distribution. And this does not happen when we do the random sampling. So sorry if this was super quick. I tried to stay in my 5 minutes. So basically, the behavior we are seeing are not due to the prior probability shift. We might have thought that this was the case, but rather there are intrinsic issues in the SLD algorithm and the generated training sets. And we are currently working on another paper which can maybe clarify for real the relationship, and maybe we can even enable the usage of SLD in these scenarios. So I have some references here, and yeah, ask me anything if you wish.
Thank you very much, Alessio.
Thank you.
Life talk, so something it needs the process. So we can take a very short break to want to just 5 minutes, or just not to delay much. Although I know this is not useful.
Thank you very much, Alice. Thank you very much, Alessio. So we are now going for a break. You may have seen that we are trying to video tube everything, although it's a little complex from swapping from one to the other. But thank you very much.
All right, thank you. Enjoy your break.
Animation will work, but still, if it
You can test it.
That's what I was.
Do it now.
Can I?
I suppose so. Though, I don't know, talk to the session chair. Il voulait tester sa présentation.
On va la tester.